Hi, and welcome back. Today we are going to talk about section 10.7, which is all about complex numbers. Now, some of you might be saying, well, math is already complex. Isn't not every number a complex number? No, it's not. In fact, all of the numbers that we've really been dealing with so far are what we consider to be real numbers. And those real numbers are things that are tangibly measurable, meaning if I were to count something or measure something, I could tangibly get a value for it. And I know there is some physical value that it is associated with. Now, that being said, there is a concept called an imaginary number. And an imaginary number is not something tangible. It's quite literally something we can only imagine. And so the only imaginary number out there is letter I, little lowercase I like so, which is the same thing as the square root of a -1. So this is the only imaginary number out there. And you might be saying, haha, I like imaginary numbers. There's only one of them. Just you wait. So when we look at the imaginary values, we have to put this into a system known as a complex number. And that is that a complex number contains both a real number value and an imaginary number value. We represent this in the format of a plus bi, where a is any value of a for a real number, and b is any coefficient value of an imaginary number. Okay, what does this actually mean for us? If I'm looking at something like the square root of -3, just to give you an idea of how imaginary values work, what I would say is that this negative is like a -1 times the square root of 3. -1 is an I value. So that would be I square root of 3, meaning my coefficient value right here, thinking about this b term, is technically that square root of 3. Now for radicals, we typically write the I in front, but if it is not a radical, the I is behind, as it is in this example. Let's try another one. Let's say I have a negative square root of a -9. This negative is completely separate, so remember that. We're going to just write it off to the side. This negative is talking about a -1 inside of the radical, and then we have a square root of 9 as well. Well, square root of 9 is 3, right? So I have -3. This square root of -1 is I, so that's a -3i, indicating this is not a real value. This is an imaginary value. Let's try another, just to get the idea of how this works. So I have the square root of -8. Again, this negative inside of the radical is like a -1. So I have the square root of -1 times a square root of 8. There is no perfect square root of 8, so you have to simplify that. Technically, this would be like a 2 times 4. I'm going to put it right here, 2 times 4 for that 8 value. And you pull that square from the 4. So that would be 2 that you can pull from here. I that you can pull from this imaginary. You're left with a square root of 2 in the radical. So a couple different formats that you can see here. We have where the coefficient is just a radical, we have where the coefficient is not a radical, and you have a coefficient that contains both a value, whole value, and a radical value. So you can see how I kind of floats around, but it is the only imaginary value, and it's simply indicating that what we are dealing with is not tangible. All right, let's do a negative square root of -81. Same exact idea. This negative out here is separate. This negative in here is that square root of -1. That 81 can be broken down. So this is 9. I have that negative still. And this square root of -1 is I, just like so. And likewise, just one more example. I have the square root of -80. And in this example, I can say that I have the square root of a negative 1 times, I'm going to go ahead and break 80 up. So I'm going to say that 80 is probably most likely people would say 20 times 4. That's usually the one I would get. 20 can also be broken up. So that's 4 times 5 technically. So hey, there's a pair of 4s. So I can pull out 4i square root of 5. Okay. Now, imaginary numbers are very easy to work with, but they can get very confusing rather quickly if you're not careful. So I'm going to erase all of this so far. I'm going to leave my complex numbers note up there because we will come back to it. But let's say I'm dealing with the square root of negative 3 times the square root of negative 7. The way you would simplify this is first pull out the I from every value that contains an imaginary value. So in this case, I have an I square root of 3. Here I have an I square root of 7. Now, multiplying this, I have 3 and 7. That's going to be square root of 21. I times I is I squared. Now, here's the funny thing about I. I by itself is a square root of negative 1. It's imaginary. But if I were to square I, that's like a negative 1 times a negative 1, like so. And so this actually converts it to a real number of negative 1. Huh. So you can go from imaginary to real. Yeah, it just got real. Yeah, I know, really corny. But that's okay, because you went from imaginary to real. That's how it works. If I were to have something like I to the third power, just to give you an idea, that's I squared times I. This is real, this is imaginary. I actually get a negative imaginary number. Interesting. And if I were to have I to the fourth power, just to go crazy here, that's like I squared times I squared. That's negative 1 times negative 1. That's actually, again, a real number. Huh. So, thinking about imaginary numbers just really quick before we go back to our problem. If I have just an odd power on my I, the odd power is indicating that I would have a negative or positive imaginary value. If I have an even power on my I, then what I'm looking at is I have a real number, either negative or positive. So, something to keep in mind as you're working with imaginary numbers. I'm going to erase it for now and just leave the I squared, since that is the one we are working with back in our problem. Now, I squared we said is negative 1, so this is like a negative square root of 21. Huh. Interesting, right? Let's try another one. Let's say I have the square root of negative 7 times the square root of negative 7. I still have to simplify by pulling out the I first from each term. Square root of 7 is square root of 49. I times I is I squared. We know I squared is negative 1. Square root of 49 is 7. So this comes out to a negative 7. Okay, now let's try another one just to see how this differs a little bit. And I got plenty of space right here. So I have square root of negative 15 times the square root of 2. I can pull out an I from here. So that's square root of 15, I square root of 15, times the square root of 2. No i's over here. Go ahead and take those. That's I square root of 30. 30 doesn't break down any further for us. So you have an imaginary value. yet again. Now, let's talk about dividing some imaginary numbers. And I'm going to get some board space here. All right. Dividing my imaginary numbers, if I have the square root of negative 75 divided by the square root of negative 3. Again, I have to simplify to my I form first, so pull out your imaginary values. And then I'm looking at, hey, 75 and 3, could I stack those and put them into a single radical? Sure. My imaginary values can cancel because it's 1 over itself. So I have the square root of 75 thirds, which is the square root of 25, which is 5. So dividing your imaginary numbers is actually very easy. What you have to do is pull out the I first and see if you can simplify from there. I'm going to do one more. I got plenty of space right here, so I'll use that. Square root of negative 40 divided by the square root of 10. I'm going to pull out my I first. Sounds very painful, but it's actually very easy. I then can say, well, I can't cancel any i's, so I know my end result will have an imaginary value. And I can see that I can simplify 40 and 10, so I'm going to do that. So I have I square root 40 and 10. This is not a root index, so I will write my I a little bit lower so you can see that. 40 and 10 can simplify, so that is going to be square root of 4, I square root of 4, which is 2I. Now, let's go back to our complex number for just a moment. Concept-wise, working with imaginary values, you can see how we use this in unique circumstances like what we've been doing. But in the real practice, we start dealing with this complex number format. So you have the real component, which you've been working with all term, and then you have this imaginary component, which we've just gotten some practice with. Now, here's where it gets really interesting. Imaginary numbers, such as this, where it's 4 plus 6i, that is the entire complex number. If I were to add this complex number with another complex number, it's kind of like combining like terms, very similar. You keep the real with the real, the imaginary with the imaginary. So 4 plus a negative 3 is 1. 6i plus 5i is 11i. And that is it. That is your new complex number from adding two complex numbers. Likewise, if you were subtracting, let's say you have 7 plus 3i. Oh, not multiplying, subtracting, there we go. Minus 4 plus 2i, like so. You're essentially doing the same exact thing. So you have 7 minus 4 is 3. 3i minus 2i is I. And there you go. Let's talk about some multiplication. Again, very similar to what you've been doing already. So if I have 6i, for example, and I'm multiplying against 4 plus 3i, you can simply distribute. This gives you 24i plus 18i squared. But I squared is a real number. That's negative 1. So that's like 24i minus 18. But there's a small problem here, only with the formatting though. The math is all correct. However, we always write our complex numbers with real, then imaginary. So we have to rearrange this. We have negative 18, that's real, plus our imaginary 24i. So this is the proper format right here. Let's try another. Let's do some binomial operation with it. Let's say I have 6 minus 4i, and I'm multiplying against 2 plus 4i like so. You can still use FOIL. It still works. So 6 times 2, you get 12. 6 times 4i, you get 24i. Negative 4 times 2 is going to be a negative 8i. Negative 4 times positive 4 is going to be a negative 16I squared. Remember, this I squared is a real term. It's negative 1, so that's like plus 16 at the end. So you have 12 plus the 16. I'm going to move it over so I keep my real numbers together. Over here, 24 minus 8, you're going to get your 16, positive 16I. So I combine these terms right here. I moved this term over because it was real. And so I have 12 plus 16 is 28, plus 16I, and I am in real then imaginary format. So I am in the proper complex number format there. Now I want to point something out. If I have 3 plus 2I times 3 minus 2I, we're dealing with conjugate values. And you know some very special things about conjugate values. They keep popping up for you. Difference of squares, basically, is what we're looking at. If we were to multiply this, let's go ahead and do FOIL. That's going to be 9 minus 6I plus 6I minus 4I squared. These middle terms cancel. I'm left with 9. This is going to be a real term now, so that's negative 4 times negative 1 is actually plus 4, and I get 13. Whoa, what just happened? How did I get a real value from complex numbers? What we did is we used conjugates. And so by multiplying a conjugate pair, such as what we just did, what you're actually getting is a real result. You're eliminating the imaginary value. And this is very important when we get to dividing. So I'm going to go ahead and clear my board space completely, with the exception of that problem. I'm going to leave that up for just a moment. And I'm going to get our first division problem up here. So I have 2 plus I over 3 minus I. And it says something like the nature of multiply the numerator and denominator by the conjugate of the denominator. You may also see something that says simplify. You may see something that says rationalize. And you're probably thinking, well, why would I rationalize this? There's no radical. But remember, I is a radical. It's the square root of negative 1. So what we have to do in this instance is we have to go through and rationalize our denominator to get rid of that radical out of the denominator. To do that, remember, you're dealing with a binomial here. You have to multiply by the conjugate. So that's exactly what we're doing. We'll come back to the numerator. I'm not worried about it, but let's work on this denominator. This is a conjugate pair, so we know that the middle term will cancel out. So I'm going to have 3 times 3, which is 9, minus, this is going to be I times I, that's I squared. I squared, though, is a negative 1, so that's really 9 plus 1, which is 10. So I've got a real value now. Cool. Now let's look at that numerator. Let's go back to it. So this is a binomial pair. I'm going to have to multiply, so that's FOIL. That's going to be 6 plus 2I plus 3I plus I squared. Remember, this is a negative 1, so that's like 6 minus 1 is 5. This is plus 5I, once I combine those middle terms. And so I have 5 plus 5I over 10. And you may be saying, yeah, I'm good, I'm done. Wrong. There is one more step, and that is you must be in the proper complex number format. Currently, you are not. So you have to split these up as 5 over 10 plus 5 over 10I. And by the way, you can simplify, so you should. So technically, this would be 1/2 plus 1/2 I. So you're in the real and imaginary format. So you're in the proper complex number format here. Let's try this one. I have 5 over 3 minus 2i. So we're going to do the same thing. We're going to rationalize our values. And so we're going to go ahead and use that conjugate of 3 plus 2i. I know the denominator value is going to be 9 minus 4i squared. I squared is -1, so that's positive 4 here, so that's going to be 9 plus 4, which is 13. I'm going to go ahead and do my multiplication up here. That's just simple distribution, so I have 15 plus 10i. It's the same thing here since nothing simplifies, so I have 15 plus 10i. Am I done? No, I can hear you now. You have to be in complex format. So you have to be 15 over 13 plus 10 over 13i, just like so. And that is your proper complex number format. Same thing that we had up here, proper complex number format. Let's try one more. I'm going to give you one more, and this one seems to usually get people. Let's have 7 over -2i. Now, as you're solving this particular problem, 7 over -2i, you might be looking at it and saying, can't I just multiply by I? No, you don't want to do that. Here's why. The denominator is technically in an inappropriate complex number format. Technically, the real value here is 0. So what does that do for me? Well, that means my conjugate would be 0 plus 2i. Takes a little bit of warping the mind for that one. Whenever you're dealing with those imaginary values, you're technically always dealing with a binomial. Even if you don't see a real component, the real component could be 0. So it is always a complex number. That's what makes them complex. All right, now that being said, we're going to go ahead and do this. I know my denominator is going to be 0 squared, which is 0, minus 4i squared. 4i squared is actually going to be a positive 4. And then here, I'm going to distribute. That's going to be 0 plus 14i. And so this would be 0 plus 14i. Split this up so that it's in proper format. You have 0 over 4, which is 0, plus 14 fourths I. This could technically simplify further, so you have 0 plus 7 halves I. Just like that. Okay, so that is it for section 10.7. I know the complex numbers and imaginary values can really take a toll on one's mind, so I highly suggest going back, getting a lot of practice in this section, especially with dividing those imaginary values and those complex numbers. Very important skill as you're rationalizing your denominators. Other than that, I will see you in a future lecture in just a few moments or as soon as you click play.